we saw in these looking at semiconductors, that the free electrons or the outermost electrons in the solid are distributed over different energies, and these can be divided in energy bands. Each band can accommodate twice the number of atoms in the solid. If you consider per unit volume, then it's twice the number of atoms per unit volume, and remaining ones have to go to another band, and between the two bands there is an energy gap. In some materials this gap is small, in some materials it is large, and some materials it is not there. As a result, there happen to be bad conductors, semiconductors, and good conductors. That's what we are talking about. So this is the configuration. We have the valence band where the electrons are there, and then there is a band gap, then there is a conduction band in which there may be no electrons to start with. In metals, particularly those who are from group 1, group 3, like you have copper, silver, gold, platinum, aluminum is from group 3. The valence band is half full. That's up to this level, that's the Fermi level here. And remaining energy levels in this band are empty, and these can be occupied by these electrons which are near the Fermi level. Once they get excited, they can go to this and they start conducting. While those from group 2 like zinc, cadmium, magnesium, calcium, etc., the two bands overlap because of the different directions. They do not give rise to any effective band gap. Valence band is full because it can accommodate twice the number of atoms, and there are 2 electrons per atom. So therefore this is full, but because of the overlap, this portion is half filled here and half filled there. So electrons are here available to go for conduction because energy levels are available in this band. And these happen to be good conductors. Again, they are not as good as these ones because the electrons have to change their direction and go to the next band because of the different direction being there. That's what we discussed in the last class. In semiconductors, this band gap is less than 3 electron volt. This is the band gap. Here I have the conduction band, here I have the valence band. This is called the top of the valence band, this is called the bottom of the conduction band. This energy level, and this is the top of the valence band. And this gap between them is less than 3 electron volts. These material elements like silicon and germanium are from group 4, and there are compounds, 50-50 compounds, which also have the similar kind of behavior. The group 4 provides 4 electrons. They go in 2 valence bands, and I can call the lower valence band the upper valence band, and it's completely full up to here. Now this conduction has to take place. These electrons have to be excited to go there, and only then they can start conducting. Otherwise there can be no conduction. Well, once the band gap is greater than 3 electron volts, these are insulators. By any means it's not possible to excite these electrons. Once this is greater than 3 electron volts, this is again the top of the conduction band, valence band, and it's the bottom of the conduction band. And the moment it is greater than 3 electron volts, they will not be able to be, these electrons from here will not be excited to reach there, and once they don't reach, they do not conduct. are no energy levels available here for them to get excited to so that they can do the conduction. These are insulators like materials oxides, diamond is one from Beaufort itself, and these materials do not conduct. Now I shall talk about the intrinsic semiconductor. Intrinsic semiconductors, by the word I say intrinsic, there is no impurities present, pure substances by themselves. No impurities in the material. That's the meaning of the word intrinsic. Now let's see, while discussing the diffraction of these electrons in the crystal, so that two localized states are obtained, one close to the nucleus, another one away from the nucleus, maybe between the two nuclei. The one which is close onto the nucleus is got a low potential energy. The one which is in between has high potential energy. Knowing this fact, we have looked at the band gap. As in other words, if I am talking about this as the valence band, as the conduction band, the electrons which are here, they are the ones close to the nucleus. And this is the one which is in between. Energy conservation better. This is what the energy of the electron. In the free electron theory, we consider total energy to be kinetic energy. We now have the potential energy when there is a diffraction taking place. Because we low down potential energy, this is a lower energy level, and this is the high potential energy, this goes there. Kinetic energy for the same, because momentum is the same for the two. And these are two which are getting diffracted. But this one with slight excitation can acquire a higher energy and will not be diffracted, will start conducting. In other words, if the electron from here can be taken to there, let us say in silicon this gap is 1.1 electron volt, let us say this is 1 electron volt. And in my solid, electron which is close by here is to be taken to somewhere between the two nuclei. This distance is of the order of 1 angstrom, the radius of the atom. And the energy is to be increased of this electron by 1 electron volt. How much more energy or electric field should I supply? 1 volt. And over the distance it has to be applied is 1 angstrom. How much is this field? By any stretch of imagination, can you prepare this field? So, my friend asked me yesterday in tutorial class, by applying any kind of electric field, I cannot excite this electron to go there. It's not possible. However, what helps us in this excitation is the thermal energy. Thermal energy provides the random distribution of these energies. During collisions, they are changing their energies and all that, and that will take care of the thermal energy. So, in practice, when this electric field is not possible, the thermal excitation is certainly possible, the probability may be small. And probability, as given by Fermi Dirac statistics we discussed earlier, 1 divided 1 plus exponential E minus EF by kT. Now, in intrinsic semiconductors, the Fermi energy lies in the middle of the band gap. probability of occupation is 50%, but there is no energy stored there. Allowed state is not there. It's a forbidden gap. There will be no electron there, right? So that's the situation. Fermi energy is here. If I want to know what is the probability of occupying this level of energy, I have to use this difference between E and EF. If I consider this to be zero level, this will be Eg. The difference will be Eg minus EF. And EF, since it is in the middle, it is Eg by 2. So E minus EF will be Eg by 2. This will become Eg by 2 kT. So Eg value, if I consider silicon, which is Eg is 1.1 electron volt, Eg by 2 would be 0.55 electron volt, and kT at room temperature, if I consider, is 0.026 electron volt, right? This is more than 20, exponential of more than 20. Which will be much greater than 1, and I can neglect this one here, and this can be written simply as exponential of minus Eg upon 2 kT. Okay, because this is brought in the numerator after neglecting 1. Right, here is my top of the valence band. This is my bottom of the conduction band. This is my Fermi level. And here is this energy axis. And this is the probability given by Fermi direct statistics. 0 here, 1 here, 0.5 here. There is 0.5, but there is no energy level here, which can be occupied by an electron. But you see, at a given temperature, it is not 0 here, while similarly, it is not 1 here, it's less than 1. So these electrons from here are in a position to get excited to reach there at a given temperature. Probability is very small though, very some. And that is why we are able to measure some conductivity of silicon and germanium at room temperature. And these are the electrons here because of this probability, and they are the ones which can be excited to go to higher energy levels and start conducting. The number is small, so conductivity is small. It's worse than the conductors which we looked at. The conductivity in the range of, or received in the range of 10 minus 9 1 meter, 10 minus 3 1 meter. These are the ones which are between the range of 10 minus 3 to 10 power 3 1 meter. Right, so that's about the thermal excitation and the distribution of thermal energy in this free electron gas. Well, I think the slide is here already. For E at the bottom of the conduction band, E minus EF going to be Eg by 2. And when I substitute this here, that's what it is coming out. And I said this is the calculation which again I am making, and that's going to say that it's going to be exponential of minus Eg upon 2 kT. That's what it is. Probability of occupation energy level is also equal to the fraction of electrons being there. And that fraction of electrons at energy E is this probability, and I call this small n by capital N. Small n is the number of electrons which are just at the bottom of the conduction band, and capital N is the number of electrons which could have been excited to reach there. There are a number of models available in physics that go into detail the work of this N. I, being an engineer, will not go into those theories, those models, those approximations. I shall try to work it out experimentally what is this number. Let's try to do that. So we define small n as the number of electrons promoted across the gap. Capital N is the number of electrons available for excitation from the top of the valence band. Right? Though I know in the valence band, if it is full, I have twice the number of atoms per unit volume as the total number of electrons. But I want to find out what is this n actually, and this promotion in turn leaves an energy level. If some electron from the top of the valence band has gone to the bottom of the conduction band, then there the energy level becomes empty. Right? If this is my valence band, this is my conduction band. Let's say this is the energy level here from where one electron has got excited and gone to this energy level here. So this energy level has become empty. And this energy level which has become empty in the valence band, I will call it hole. Like we call it vacancy in case of vacant sites in the lattice. This one we call hole. And this hole can be occupied by some other electron which is lying below. It can come and occupy this. In turn the hole will go down, the energy level. While getting excited, electrons in the conduction band travel and go to the higher energy levels. When get excited, the holes start traveling downwards, go to lower and lower energy levels. It is as if electron is of a negatively charged particle, we know that, so hole is a positively charged particle, and moving in the direction opposite to the electrons. And that is how we treat it. Okay? Therefore, in an intrinsic semiconductor, number of electrons in the conduction band is equal to number of holes in the valence band. Right? So, is equal to number of electrons in the conduction band of holes in the valence band. And we also put this, these are equal, we put this equal to Ni, number of intrinsic charge carriers. Now, under an externally applied electric field, this electron can get excited to go to high energy level. You see the energy difference between the two levels that we worked out earlier is a bit order 10 to minus 34 joules. It's a very small energy. And the electric field can provide that much excitation. And they can go to high energy state and therefore start conducting. So when I apply an external field, the electrons in the conduction band go to the high energy states and they start conducting. Similarly, the holes start going to the lower energy levels because they get occupied by an electron which is lying somewhere down, and they start moving down. However, they also start conducting. So both holes and electrons are conducting. They are carrying a negative charge with them and they are carrying a positive charge with them. Okay? So both electrons and holes conduct. Electrons in conduction band and holes in valence band conduct. And we are conducting electricity, that's what we are looking for. conduction in a new semiconductor is due both to electrons as well as holes, and that component of conductivity due to electrons in a conduction band is this. This is the number of electrons per unit volume, this is the charge on the electron, and this is the mobility of the electrons in the conduction band. This is what is happening in the valence band. Number of holes in the valence band per unit volume, charge is the same as the charge in the electron, because what is happening is electrons are coming and occupying the holes essentially, they are the conductors. And holes, this is the mobility of holes. This mobility of holes is different from the mobility of electrons. It is rather less mobile as far as holes are concerned, because the hole has to be occupied by an electron from a lower level by excitation. It can also be occupied by an electron from a higher level by lowering its energy, because thermal excitations can always do that. Therefore, the net movement is really decreasing, and it's not really as much. But in the conduction band, the higher energy levels are all empty. Any electron can get excited and go to higher and higher energy levels and start conducting, right? So their mobility is more. So number of electrons in the conduction band and number of holes in the valence band are equal, which are called the intrinsic charge carriers, times the charge on the electron and the mobility of the electron plus the mobility of the hole. I will show you this mobility of the electron and holes are somewhat given here. You can see that electrons in silicon have a 0.14 meter square per volt per second, while holes in silicon have 0.05, so about one third. And germanium is 0.39 for electrons in the conduction band, holes in the valence band is 0.19, is almost half. So that's the mobility of these electrons and holes at room temperature, and the temperature dependent near about room temperature is very marginal, and we don't consider it, we consider it to be constant. Now that's the question which I said I would like to estimate this n, number of electrons available near the top of the valence band which can be excited to reach the bottom of the conduction band. To do that, we do experiment at room temperature, measure its resistivity, it turns out to be 3000 ohm meter. And conductivity, which is sigma, is 1 upon rho. And that's Ni times E times mu E plus mu H. Substituting this, it is possible for us to find out the intrinsic charge carriers. And that's what we work out turns out to be 1.095 times the 16 per cubic meter. This is the band gap, and the electron to be excited from here to reach there. Let's say these numbers which are available here is n. The probability it can reach there without is exponential minus Eg upon 2 kT. Yes, written other way around. So Ni, the one which I have gone there, is capital N times exponential of minus. I am interested in finding out this, how many of these. So that's how I rewritten it with a plus sign there. And I worked out this number turns out to be, after substituting this Ni, Eg is known, K is known, T is room temperature, it is 1.68 times by 25 per cubic meter. What fraction is this of the total number of electrons available in the valence band? Okay, let's look at that. Number of atoms per unit volume of silicon is easy to find out. In a unit cell there are 8, effective number is 8. try to work it out now. And the lattice parameter of the diamond cubic silicon is 5.43 angstrom. This is the volume is 5.43 10 minus 10 cube meter meter cube. So per cubic meter I have so many silicon atoms, 5 10 power 28. So the valence band, how many electrons do I have? Double of this. Power are there in the lower valence band, okay? It's not 4 times, it's only 2 times. So it is 10 to the power 29 per cubic meter is the number of electrons in the valence band. Out of these, what can be excited is 1.68 10 power 25 atom temperature. What fraction is this? .68 10 power minus 4. It's a very small fraction. 0.00016 or 0168, you can call it 02 if you want, which means about 0.02%. So very small fraction of electrons available in the valence band can be excited to go to the conduction band. That's the meaning of it. And well, the numbers which have been there, the models which have been worked out also give probably a similar result. Next, which I want to look at this guy, since there is a thermal excitation which is taking the electrons from the top of the valence band to the conduction band, its conductivity will be affected by the temperature. And as you recall, while discussing the materials, I said these are the materials where conductivity increases with increasing temperature, while in case of metals, the conductors, it decreases with increasing temperature, right? That's what we are going to look at now. Conductivity is a function of temperature. It can be written as this number of charge carriers, n times exponential minus Eg upon 2 kT. This is a charge and the mobility of the electrons in the conduction band, mobility of holes in the valence band. So small ni has been written like this. Capital N exponential minus Eg upon 2 kT. Now I take the constant terms on one side and temperature term on the other. So capital N is a constant, E charge is a constant, mu E plus mu H again. I take the temperature dependence to be very marginal and therefore not considered temperature dependent, and I put constant. This is put as a constant and becomes exponential minus Eg upon 2 kT. And when I take the logarithm of this, I take logarithm of sigma is equal to logarithm of a constant minus Eg upon 2 kT. Right? So if I plot the logarithm sigma versus 1 upon t, I get a straight line with a slope minus Eg upon 2k. That's the meaning of this equation. And if you work it out, experimental logs, you get this. Logarithm of sigma on the y-axis, reciprocal the temperature on the x-axis, you get this straight line and the slope is minus Eg upon 2k. It's a straight line. And this information is what you can exploit if you want to use a semiconductor as a thermometer to measure the temperature. With the workouts, conductivity at one temperature, we get it at another temperature like this, and from which can be calibrated to temperature. Because this is there, this is reciprocal temperature. You want directly in terms of temperature, you can do that. So that's how you can exploit this and can use this as some of the thermometers are made of semiconducting materials. shall talk about the semiconductors which are extrinsic in nature, means some external impurity has been added to these, and those impurities are the ones which are influencing the conductivity. While talking about conductors, I did tell you that when the impurities are added, the resistivity increases, and these impurities, substitutional impurities or the interstitial impurities, are very bad in doing the job. That is, metals. I'm talking about metals and conductors. Here you will find it other way around. When you add impurities, they increase the conductivity. Okay? In extrinsic, we call it extrinsic because the conductivity or conduction is due to the presence of the extraneous impurities. These extraneous impurities we add knowingly to a very pure substance, intentionally, and therefore addition in a controlled quantity is called doping. And all the processes of diffusion we talked of are the ones which are exploited. Whether material is deposited on the surface, then it is driving inside the material by heating, or you can put the semiconductor in a gaseous atmosphere through which you can allow the impurities to go in, and you do this for a certain length of time at a given temperature to get a certain concentration of the impurity at a particular position in the solid. Okay? That process is called doping. Impurities which we add generally for pure elemental semiconductors, as we said, the silicon and germanium, and more commonly what we use is silicon, elemental semiconductor. Germanium really we started with, in 1948, the semiconductors we started working with, and slowly we found that handling germanium is not so easy. It's rather a difficult process because germanium oxide, oxide is normally the one which we use for insulating the two components on the chip, is soluble in water. While silicon oxide, which is from SiO2, is not soluble in water, it's a good insulator. It can be used for isolating two components on the chip. And therefore we found that silicon is a better material, we continue to use silicon. Anyway, elemental semiconductors we have are silicon and germanium. To make them intrinsic, extrinsic, we add impurities, and generally either from the left of this group 4 or from the right of the group 4. When I take from the right of the group 4 as a group 5, impurities like phosphorus, arsenic or antimony, these are added. Right? Say for example, I am showing them at 90 degrees. We know that they are not at 90 degrees. The bonds are at, sp3 bonds these are. Where is my eraser? So on and so forth. There are 4 bonds to every silicon. And silicon is bonded like that. So let's say I write phosphorus in one place. It also forms 4 bond sp3 bonds. But being from group 5, it is a 5 electrons in the outermost orbit. So this positive ion of phosphorus takes part in bonding, and if the size of that orbit is what I will just make a very crude estimate of that. We've done this in school, the Bohr radius in hydrogen, if I am not doing that. Electron orbiting around the proton, which is the hydrogen nucleus, has a radius which is worked out using n as a quantum number 1. H square is the Planck's constant. Epsilon 0 is the dielectric constant of the free space. Pi is the constant of the charge, and is the mass of the electron. And that gives me the hydrogen, or the radius of the orbit in hydrogen for the one electron is 0.53 angstrom. Now when I convert these for phosphorus in silicon, well, the positive ion core I can just consider like the proton of hydrogen. Then the electron, the fifth electron, which is this, is the our quantum number will be 1 for that. Planck's constant square. Instead of now the dielectric constant of the free space, I use the dielectric constant of silicon. This is the relative permittivity, and this is the dielectric constant of the free space. So the product will become the dielectric constant of silicon. That's a constant pi again E square, and this is the effective mass for this electron. I am not considering the mass of the electron. I'll tell you why I am not considering is it is close to that position where it gets deflected. And all those electrons which are close there by have to be used effective mass. Alright, so here the other terms are there except these two terms and this mass. So mass divided by this is about this 0.1. Effective mass divided by the and this dielectric relative permittivity is 16, and therefore rest of it is 0.53, becomes about 80 angstrom. Angstrom is the radius of the orbit for this fifth electron around the phosphorus. From the phosphorus atom to the electron, how many silicon might be there in between? Divided by diameter of silicon. And how much will be diameter of silicon? Any estimate? Guess? Take 2.5 angstrom safely. We will go around that. Right? So if I take 2.5 angstrom, how many will be there? More than 30. More than 30. It's very far separated from the phosphorus already and is orbiting around. In other words, what I am trying to say is to take it away from this orbit, in other words, away from the phosphorus, I need to put a very small effort. I need to put a very small effort to take it away from this phosphorus or make it free from the phosphorus. Once it is freed, it can travel in the solid silicon anywhere like a free electron. And that small excitation which is required is what I'll show you here. This is the valence band of the silicon. This is the conduction band. This is the energy level at which this electron is from the donor. Phosphorus is called a donor because it has donated this electron to silicon. Now this energy difference between the bottom of the conduction band and this energy of the impurity, energy level of the electron of the impurity, is very small. It's called the ionization energy of phosphorus in silicon. If I provide this small delta E, this phosphorus will have been ionized. That means it will remain like silicon bonding there, and this electron is free to move around. That means it has reached the conduction band and can conduct. That is why the conductivity goes up. It has not affected the number of holes in the valence band at all. It has only provided me electrons in the conduction band. Really speaking, right? That's what has happened. Okay?
So this energy level shown in blue color, this is for
energy of this electron which is provided by the phosphorus, the fifth electron of the phosphorus.
So where does the Fermi level lie now?
Yes, I'll come to that. At 0 Kelvin, Fermi level is close by to this the energy level of the different color. Here. And as the temperature rises, this goes down and come to the middle of the band gap. By the time it reaches high temperatures. It's a function of temperature, this Fermi level. Fermi level at 0 Kelvin is close by this, and then it goes on decreasing, goes to the middle. What has happened at that temperature you have reached, I'll show you that. Now the temperature is enough for the electrons from here to get excited in large number to reach there. And this number becomes very small, meager as compared to the ones which are coming from there. So it becomes an intrinsic conductor. Impurities have really no role to play after that. Impurities are playing role at low temperatures only. Okay? Right. So that's very high temperatures. This number will be so high that will be overtaking these electrons which are can be excited from here. Now second thing, so far for working on the probability of occupying the energy levels at the bottom of the conduction band, I use the Fermi-Dirac statistics. But for the excitation of these electrons of the impurity to go from here to there, so very small energy level, we use the Maxwell-Boltzmann statistics. And the probability here would be exponential of minus delta E by kT. Delta E is the ionization energy. Right? And now the electrons get excited from here, go there, start conducting, and the number of impurities which you are provided here that you know, probability you can find out n. This is less by delta E. So some of the electrons will be able to come here. Now there will be some holes produced, and those electrons can also get excited in time, in the course of time. In other words, there will be some holes in the valence band too. That law of mass action provides us the number of electrons in the conduction band times the number of holes in the valence band is equal to the square of intrinsic charge carriers at that temperature, whatever this number. So this is another result which I am just taking from this law of mass action, and using it, it's possible for us to work it out. It's not impossible for us to work out what is getting excited to reach there and what is getting excited to reach there. Find out those two numbers, find the product, find this to be Ni square. Alright, this is the electron provided by the impurity to the conduction band, why I call them donors.
so why can't we use group structure rules?
Pardon?
So why can't we use group structure rules?
Why can't I use group 6 elements? Okay, but they are providing 2 electrons, not 1. Right? Now we have to take care of that. It's possible, it shouldn't be impossible to do that, but normally we are using O5, only one electron, you can take care of this. Your models can work well because there will be two, I don't know, I have not come across the models for those two, and we'll have to work out. Possible to work out, you can use that. Okay?
What is
Because
capital N in this exponential? It won't be capital N.
this one, this I'm talking about impurity, so this is number of impurity atoms per unit volume. Or we want to call it donor and some D. So we will not confuse with the other capital N which I talked about, the thermal excitation.
Sir, if it had been an intrinsic conductor, then Ne equals NH equals Ni.
Yes.
Here we have Ne is also increased and NH is also increased.
No, NH is not increased.
But
NH
we have
is not
an
increased.
extra level created at the donor level, so there will be more holes that are produced.
You see, it is like this. This number is so high, which is provided by the donor. What is coming from here is not possible because that will be able to go first here and then get excited there. So the holes which are produced is not equal to this. Are much smaller.
They will be smaller, but they will be larger than that in the case of intrinsic, na? Because now from valence bond electrons can go to both conduction band as well as the extra level.
I agree with you, but what you have to do is you have to find out how many can be excited from here to there, and whatever you have getting excited from here to there, find the product, it will turn out to be this. There is no effect on this. So in this case of impurity, the problem is the Fermi level is here. And in the case of intrinsic, the Fermi level is here. That's making the difference. Once I have the impurities, I have to have my Fermi level there. And if I use that as a Fermi level, then excitation of the from here to there also I use the Maxwell-Boltzmann statistics. From here to there also I use Maxwell-Boltzmann statistics. But once my valence, the Fermi level is here in the intrinsic area, I am using the Fermi direct statistics to take it from here to there. That's where the model seems to be working with the experimental results, Alright, so that's what we are talking about. The size of the orbit around the phosphorus nucleus is very large. And the small energy is required to excite this electron to go away from the phosphorus and become almost a free electron in the silicon. Then if we take element from group 3, these are called p-type impurity because the charge carriers here are the positive charge carriers. Not the electrons but the poles. And these p-type impurities are also called acceptors because they accept electrons. Right. Again, let's look at this. Alright, now let's put this one as, let's say, boron. It has only 3 electrons. But it has to take part in the sp3 bonding. So one bond only 1 electron. Sharing is not complete. For this, electrons can come from the neighborhood. And from how far this electron can come here. That can be worked out in the same manner as we worked out for the phosphorus. That is the distance of the orbit from the nucleus. Same way you can work out how far it can come with a distance of about 80 angstrom. this electron can be provided to form a bond here. And wherever it is coming from, it is moving there a lone pair in the bond. Okay? And that's where the electron from the neighborhood can always come. Now the situation is slightly different. Here I have my conduction band, bottom. This is the top of the valence band. The energy level here, now for this, is somewhere here. And once again, the Fermi level, the low temperature is here, keep on increasing, the high temperature will go in the middle of the band gap. So the Fermi level as a function of temperature. So now these impurity levels which are present here are accepting electrons from the valence band. This energy is very small again. Boron is accepting the electron and thereby getting ionized. Phosphorus has given out the electron and got ionized. This is accepting the electron and getting ionized. And this ionization energy is again small. Very small value, and therefore you can find out how many electrons from here can come there. Almost all the impurities can be ionized depending upon what the temperature is. Even if, as I said, 99.8% and 9% is ionized, I consider it to be almost 100%. Right? That is possible. Now it shall leave here holes. And what is going to conduct other holes? Additional electrons are not reached there. Once again, we have number of electrons in the conduction band times the number of holes in the valence band is equal to Ni square. That remains the same, and similar is the behavior of the phosphorus. The conductivity as a function of temperature, now if I look at, this is reciprocal of the temperature. In these impure materials or doped materials, whether they are N-type or the P-type, in general the temperature ranges for the different stages could be different, but this is the, by and large, independence. You see that as the 1 upon T increases, the temperature is decreasing, becoming smaller and smaller. At infinity it will be 0 Kelvin. This is the extrinsic semiconductor. The slope provides me is minus delta E by K. Delta E is the ionization energy, K is the Boltzmann constant. Right? So basically they are in the, actually I say sigma for N-type, it should be number of electrons in the conduction band E times mu E. Second term will be negligible. Similarly, this is for the donors or N-type, and for the P-type the same thing would be then as the temperature rises, you reach a stage where all the impurities which are present have been ionized. There are no more impurities cease to be ionized, and whatever conductivity you have reached will not change with increasing temperature. That's called the exhaustion region. I have exhausted all impurities. Now I have, if it's an N-type, I have all electrons in the conduction band, and they start behaving like free electrons in the conductor, and the conductivity decreases with increasing temperature. It's a metallic behavior. Then we reach a temperature which is very high for the electrons from the valence band to get excited to reach the conduction band, and it becomes an intrinsic charge carrier or intrinsic semiconductor, the slope being here minus Eg by 2k, which is very high slope. The very high slope here. So impurities have no effect really when the temperature becomes so high. Fermi level has already come to the middle, and when that happens, then there is no effect of the impurities present. Right? This is how the conductivity changes with N-type and the P-type, and a function of temperature. If you want a material to be used which provides almost same conductivity over the period of time, the ambient temperature might be changing. It is the exhaustion region which you should exploit. Resistivity would remain same, conductivity would remain same within certain temperature range, and you can exploit that temperature range for this material to be used. If you want to use it as a thermometer, this is the right region to be used it as a thermometer, because sensitivity is high, slope is high, the sensitivity would be more. Right? Well, that's about the applications. We shall see in the next class.